All right, so let's do an example of partial fractions together. And in fact, we're going to use the example from before, this 2x over x squared minus 2x minus 3. And we're also going to see this in the form of an integral. And the big thing I want you to notice right away is we're just going to set that integral aside to kind of the very end of this problem when we actually integrate those easier pieces. So in terms of partial fractions, the first step we do is factor the numerator, or factor the denominator, excuse me. So in this case, when we factor that denominator, this denominator factors rather nicely for us into an x minus 3 and an x plus 1. So that's all we do for the first step. The thing we also do in this step is start noticing things like, oh, in this case, we have distinct factors in the denominator. Because we don't see any x minus 3s to the second power, we just have x minus 3 to the first and x plus 1 to the first. Step 2 in this case, for our partial fractions decomposition, is actually laying out what the decomposition looks like. And as we discussed in class, the decomposition will ultimately depend on what type of terms we see in that factor denominator. Now, in this case, because that denominator has distinct factors, this puts us into a specific type of partial fractions decomposition where we only need to write some unknown, in this case, we'll call this a, sitting on top of one of those factors, say x minus 3, and we'll add to it another factor, say b, which is an unknown coefficient, all over the other distinct factor in the denominator, the x plus 1. So here I just want to point out that these two are unknowns that we'll solve for. And the way in which I think about partial fractions decomposition is sort of like this thing on the left-hand side, our rational function to begin with, is sort of like a cake, if you will. And then on the right-hand side, we have the individual ingredients that make up the cake, say 1 over x minus 3 and 1 over x plus 1. And those unknown coefficients in the numerator, a and b, are sort of like the amount of ingredient we actually need. So it'd be like saying 2 cups of flour and say like a half teaspoon of butter or something. So at this point, after we finish writing out that decomposition, we can go to step 3, which is figuring out what those unknown coefficients are. And the way in which we do that is we take the previous line, which I'll just write out again. We'll cross multiply in one moment. Or in other words, we will multiply both sides of that equation by what we saw in the denominator in the rational function. So we'll multiply both sides by x minus 3, x plus 1. And remember, we're abiding by rules of equations, as in what we do to one side, we get to do to the other as well. Here we're multiplying both sides by x minus 3, x plus 1. So on the left-hand side, all those terms cancel out, and we're just left with the 2x. On the right-hand side, when we distribute the a over x minus 3, well, let's actually just write it out. So we'll have a over x minus 3 times x minus 3, x plus 1. And then we'll have, adding to that, the other term, b over x plus 1, all times x minus 3, x plus 1. And we'll see that in each of these terms, that in the first term, the x minus 3 in the denominator cancels out that x minus 3 getting multiplied on. And in the term on the right, the x plus 1s cancel out. So what we're actually left with at this stage is 2x is equal to an a all times x plus 1 plus b all times x minus 3. And what our actual goal is, remember, we have two unknowns in this equation. We have this unknown a, and we have this unknown b. We're trying to figure out and solve for those. But because we have two unknowns, what that ultimately means mathematically is we need two equations in order to solve for those two unknowns. So let's just factor or distribute that a into the x plus 1, that b into the x minus 3. So we'll get a times x plus a plus bx minus 3b sitting on the right-hand side there. And if what we really want to do then is we can group all the terms with x's on the right-hand side, the terms without x's. So we have 2x on the left. We'll have an quantity a plus b all times x, that coming from the ax term there and the bx term over here, just grouping those together into that one term. And then we can add to that the other term that just includes kind of just numbers without any x variables. So we have a minus 3b. I'll just put parentheses around it just to denote that grouping. And remember, a and b are just some unknown numbers that we're trying to solve for at this junction. So we treat them as though they're numbers. We just don't know their true identities yet. And this is where we can actually sit and think about this equation for a few seconds. What I want us to realize is the terms with the x's, well, if we have an x term on the left and x to the first on the left, we have an x to the first term on the right, what that means is those terms must be equal. Similarly, terms without x's on the left must equal terms with or without x's on the right-hand side. So what we're actually going to do now is group by powers of x. So, for example, if we look at and we'll look at this in terms of the left-hand side and the right-hand side. So the first thing we'll group is let's group all the terms that have x's in them. So the terms on the left-hand side that have the x's, well, that's 2x. But since we're just grouping those terms, we just have a 2 on the left-hand side, since we're already knowing that that term has an x attached to it. While on the right-hand side, what that means is we need the term that has the x on it, which would just be the a plus b. So we can set a equal to, or sorry, 2 equal to a plus b. And those are all the terms on the left and the right that have an x. If there were terms with x squareds on the left or right, we would do the same exact process. So now what we can do is group the terms without any x's, or x to the 0th, since what that actually means is anything to the 0 power is 0, or is 1, excuse me. So this would be like grouping our constants. So on the left-hand side, there are no just constant terms on the left side of this equation. We just have a 2x there. So what that means is the left side of the equation, we can put a big old 0. Since there are no constant terms, there are only terms with x's. While on the right-hand side, what that means is the terms without x's would just be that a minus 3b term. And lo and behold, what we're able to just do is figure out that we actually do have two equations for two unknowns at this point. So we can go ahead and try to solve for a and b now because we have these two equations at our disposal. So from this, what we can do is some substitution methods. So for example, from the second equation, 0 equals a minus 3b, we can solve for a just by adding 3b to both sides. So let's do that together. We have 0 equals a minus 3b, then we get 3b equals a. So our first relationship that we know is we know that wherever we have an a, that's also the same thing as 3 times b. Then what we can do is substitute that information into the other equation. So what I mean by that is we have 2 is equal to a plus b. And well, what we figured out a was from our relationship above is we saw that a is the same thing as 3 times b. So we can just substitute that in for a. And why that's convenient for us to do is, well, next we get 2 is equal to, what that right-hand side is 4 times b. So when we go ahead and then divide both sides by 4, we see that b is equal to 2/4, or b is equal to 1/2. And now why this is convenient is because, well, from our original relationship up above again, coming back again to this a is 3 times b quantity, we know immediately what a should be. So since we saw before that a is 3 times b, we know that this is 3 times 1/2. So a is equal to 3/2. So step 4 in our partial fractions is putting this information together. So if you remember from above, just grab this information. We had that 2x over x minus 3, x plus 1 is a over x minus 3 plus b over x plus 1. And well, now we know the identity of a and b. So we know that, in fact, 2x over x minus 3, x plus 1 is equal to what we saw for a, which is 3/2 all over x minus 3, plus b, which we saw was 1/2 over x plus 1. And that is how we can figure out the partial fractions decomposition of rational functions. Now, the original problem called for us to do an integral. So in fact, if we're thinking about that integral, adding those integral signs to both sides, and integrating with respect to dx, I don't know about you, but I would much rather integrate what's on the right-hand side of that equation. Because, well, of course, I can break these up into individual integrals, and what this turns into is 3/2 times the integral of 1 over x minus 3 dx, plus the integral, or plus 1/2 times the integral of 1 over x plus 1 dx. And hopefully we're starting to see that these look like the antiderivative, or these are looking like integrals whose antiderivatives look like logs, or natural logarithms. So computing these integrals, the first one we would get is 3/2 times the absolute value of the natural log x minus 3 plus 1/2 times the absolute value natural log of x plus 1. And then don't forget our friend plus c. And that is the antiderivative of that rational function we first considered. So again, the big part of these problems is really this algebraic manipulation of that rational function. Once we get to the integral or the integration step at the very end, hopefully those integrals are rather straightforward.